represented on this slide right here at the bottom right, with that Q loss value. The purpose of this table. So the idea was this. If you drop any object from a given height, you're dropping it with no velocity, so it starts with no kinetic energy, no velocity to start. It has a certain height to start. That certain height that it has to start is 1 meter. This is literally the Super Bowl experiment right here when you think about it, the drop from 1 meter. The potential energy is a certain value because it has a height. And the total energy is all potential in the beginning. Okay, so remember for these types of problems, if you scroll up in your notes real quick, you'll see from last time that we quickly, oops, let me make this work. Okay. We quickly talked about here, why is that not moving together? Some new settings on this thing. That doesn't allow it to move. Can I reset it? There we go. So we quickly talked about the pendulum and how it has potential, has both, has only kinetic, has potential. We saw the example. And it's the same thing with this table here. So what we really want to recognize is that in this table, the total energy is constant. And here's the total energy right here. It's never changing, no matter where the object is. So this is when it's dropped at 1 meter, then it starts to fall a little bit further. It falls, so it loses height, and therefore loses potential. It gets faster, so it gains kinetic. It continues to gain kinetic the whole way down. It continues to lose potential the whole way down. As it's falling, it's losing potential. But if I add these numbers, with this exception right here, if you round this one properly, round this to 0.04. I don't know why they didn't round it to 0.04 if everything else is rounded. But if you add these two numbers each time, you still get a total energy in the system of 0.74 joules. So whatever we start with, we have at any moment in time. And that's the whole concept of conservation that we're going to now apply to these examples.
So if you have talking about the pendulum, if you have one instance of the potential and kinetic energy, then you have the energy.
Correct.
Right?
Absolutely.
The
Absolutely, Chris. Great point. So Chris makes a really good point. So if I said to you guys that in this diagram, we didn't know the starting potential energy, but we knew that the potential plus kinetic at this moment was 6, we can assume that this is also 6. And we're not assuming, actually. We can make a clear statement that it is 6. We can conclude that it's 6. If I tell you that the kinetic energy at the bottom for a pendulum is 6, you can conclude that it's 6 anywhere else along the way. And that's what this whole idea is saying. So if you know the energy in the whole system at any moment, it's the same throughout time. It's not going to change. The energy is conserved. When we see a loss in energy, we'll talk about what's called Q loss. And that is represented, if you recall, on the previous slide. Okay? But let's get into this so we can see examples itself. So for the first one, starting from rest, the child slides down a frictionless ramp on a skateboard. If the height of the ramp is 4 meters, then determine the speed of the child at the bottom of the ramp. First thing to do for all problems is to figure out what your potential energy zero line is. Or you remember your ground level, we called it, ground level. So for a problem like this, for any problems going forward, my recommendation is calling ground level the lowest point of the object in the scenario. So in this scenario, the child is starting at the top of a ramp, sliding down the ramp on a skateboard, and then we're trying to figure out the speed at the bottom of the ramp. What happens after the kid hits the bottom of the ramp? What happens?
Potential energy 0.
Potential energy, if we call the ground there 0, very good, at the bottom of the ramp.
The speed decreases after that point?
There might be some friction in the floor, so the speed can decrease. But my point is this. It doesn't matter what happens after the child hits the bottom of the ramp. Because our problem starts at the top of the ramp and ends where? At the bottom. We're trying to figure out the speed at the bottom. Unless the problem continued and said part B, now the child with that speed enters a surface and the friction coefficient is this much, when will he or she stop? That could be like a second part of a problem. Again, more of like an AP level problem or an advanced problem where you're going to combine friction from last chapter or maybe combine work with the conservation of energy here. Not an impossible problem, but a little bit more difficult in that sense. So here let's start by drawing a quick diagram of what's happening. So let's draw what we think of as like a ramp. A ramp could be linear, it could be curved, whichever way you'd like it to be. We're going to start with a quick ramp. So maybe I start with this as my ramp. right? Because if you think about like a skater, usually it's like a half pipe kind of shape. It's not actually a ramp unless they're landing on like a table, which would be flat. Or again, obviously we can make the ramp like this, not as realistic, but also the same thing. I want to prove a point in this problem that it doesn't matter which shape we choose. Which is kind of crazy to think about, actually. Now, the time it takes to get down the ramp will change depending on the shape. One of these options is better than the other if you want to get down a ramp as fast as possible. But the speed at the bottom of the ramp is independent of the shape. The shape does not affect the speed at the bottom of the ramp. And let's prove why that is with energy. So depending upon which ramp I have, again, it doesn't matter. I know that the height is 4 meters above where the bottom is. So that's my overall height in either case. It doesn't matter which ramp I'm referring to. And again, at the top of the ramp, the skater starts from rest. Starts from rest. So what kind of energy doesn't the skater have, or does the skater not have in this problem? The skater does not have kinetic energy to start, because he or she starts from rest. But he or she starts at a given height, so therefore this person has what kind of energy if they start at a given height? Potential energy at the beginning. So either way I look at my diagram, whether it's curved as a ramp or linear as a ramp, it's the same setup to start. Chris?
So at the top and then at the bottom, wouldn't like the potential energy initial equal like the kinetic energy final?
Why would that be?
Because like there's no potential energy at the end if they equal the same.
Yep, and that's where we're going to lead to with our formula. Absolutely. So we're going to extend to that point. But before I get to that point, Chris, let's mark off our ground level. We have to do that first. Because without ground level marked off, we don't know if the bottom of the ramp is going to have potential energy or not. Now, maybe this bottom of the ramp then continues and this ramp goes off of the side of the building and the skater goes down further. Then the potential energy ground level line has to be down here, right? Because that's the end of our problem. But because our problem in this case ends at the bottom of the ramp, I'm going to put a dashed line to represent ground level. And I've been doing this over and over, and I've been calling this the potential energy zero line. And the rationale behind that is if you write PE equals 0 there, it pretty much tells the reader, me being your grader on the test, that that's ground level for you. If that's your ground level, then you can come up with your next part. Without that statement, technically, I can't even grade your problem. I might be nice and try to figure out what you're doing, but I probably deduct points if you don't have this somewhere. I'm telling you now. Because if your potential energy ground level were here, it totally changes the problem. Because as Chris said just now, if that's ground level, then at the end of the problem, the skater, he or she, has kinetic energy. But he or she does not have potential energy because the skater is now at ground level. So there is no potential energy at the bottom of this problem. But if the bottom of your problem, or if the ground level, the way you think about it, for some crazy reason, in this problem you would never do this, but hypothetically, if you called ground level 2 meters below, where my hand is right now, then the object would still have potential energy here, and we'd have to take it into account. So it is really important to designate what ground level is for all of these problems when they involve any potential energy or conservation of energy in general. Okay? Now, with that statement, Chris, we can take into account what you said. At the beginning, the skater has potential. At the end, the skater has kinetic. And I showed you that little simulation of the skater going back and forth in the skate park, and you saw how the energy kept going up and down. I did that quick simulation with that FET example. You're going to actually work on that in the second period today to show the numerical values. You can see a little bit better and where heat loss comes into play. So we've got potential energy in the beginning. That's going to replace MEI. And we've got kinetic energy at the end. That's going to replace MEF. Remember, whatever energy the object has in the beginning goes right here. And it could have multiple types of energy. Think about an object, ready? Think about an object starting at a given height, but with velocity now. How would it change up this problem? An object starting the same way it starts here from a given height, but not from rest anymore. Starting from a given height of 4 meters, but it's starting with some initial velocity. Michaela.
So then we know potential. So the ground would be.
Still starting from the same height. I'm not changing that at all. But now not starting from rest is what I'm saying. Up or out?
Would you have to add the kinetic energy?
You'd have to add KEI in the beginning, because if it no longer is starting from rest, it means it has velocity. If it has velocity, it's got kinetic energy in the beginning. Because it still would have height in that case, it would still have potential energy. At the bottom, it would run out of height, so it would only have kinetic energy at the bottom still. So the alteration would be that you would add KEI in the beginning if it had some initial velocity. Because it has no initial velocity, because it starts from rest, we know that the kinetic energy in the beginning is equal to 0. That's the reason we could set the kinetic energy in the beginning equal to 0, because it starts from rest. So again, if it didn't start from rest, we'd have to tack on KE initial in the beginning part of this problem. Yeah?
Where's MPI from?
That's the governing equation from last class. It's the go up 2 slides. Conservation of energy tells me that the mechanical energy initially is equal to the mechanical energy at any moment in time. So that's the pendulum or the egg falling. ME is like the total energy.
Okay.
You can write down total energy instead of ME. That's fine. Okay, total energy. Total energy in the beginning equals total energy at the end. Thus, conservation of energy. Okay, conservation. Conservation simply means it's conserved, right? It's not lost nor gained, it's just transferred. So in this problem, if I look at it, it looks at first now like I'm a little bit stuck because I'm not given mass. Anybody see mass anywhere? It's not given in the problem. Yet these formulas both involve mass. So how am I going to approach this problem if I'm not given mass, but the formula for PE is mgy, the formula for KE is 1/2 mv squared. I know that. It's in my formula sheet. It's on the last set of notes from 6.2. So how's it going to work, Alex? What do you think?
Cancel them out.
The mass is on both sides, and both sides of this equation are products. So that means that my mass will most likely cancel out. Let's go ahead and fill in our formulas. This is mgy. I'm going to call it yi because it's initial again. Remember, my subscripts carry down. If I have a starting potential energy, it's because I have a starting height. At the end, we have velocity, and that's what we're trying to search for. So I'm going to call that VF because it's the velocity at the end of the problem. Whereas the velocity at the beginning of the problem was 0. This object started from rest. At this point, I can cancel m on both sides, making my formula simplify to GYI equals 1/2 VF squared. I like that I see people going for the calculator. You can go ahead and calculate this now. Again, we're looking for the velocity at the end of the ramp. So if you want to plug in numbers at this point, you can. Or if you want to solve algebraically, you can. I'll do it both ways here. So plugging in numbers, this is what it would look like. Solving algebraically, yeah, we get root 2GY. That's the same equation you get from kinematics, by the way, and I'll show you that in a minute. It's kind of amazing to see. That's how awesome physics is. You do it kinematics or energy, you get the same results. So again, I can solve this problem 2 ways. I'll separate it so you guys can see it. Okay, I can solve it this way here with numbers by plugging in and then just getting VF. Or I can actually solve for VF by getting rid of 1/2, multiplied by 2, puts the 2 up here. Get rid of the square that's left on VF by taking the square root, remembering plus or minus there.
Do we leave in plus or minus the answer?
We'll talk about that. For now you can.
It has to be a positive, right?
We'll discuss. We'll discuss. Yeah, there it is, Dennis. Good. Dennis, notice it says speed, so it is going to be positive because it says speed.
Right.
But let's talk about what it would be if it said velocity. What do I get as a number here?
8.9.
8.86.
Yeah, 8.8.
Yeah, like
really
really fast. Yeah, isn't that like super fast?
Meters per second. Well, 4 meters is 12, around 12 to 15 feet. So this is the max speed the skater would have. If this were a half pipe, that's the speed at the bottom of the half pipe. And then what would happen to the skater on the way up?
Oh, go back down.
It would slow down.
Oh,
It is. That is a very fast velocity, but it's not unrealistic at all. 9 meters every second. It's far. It's like 27 feet covered in a second. But it's because the skater would be going really fast. And what are we assuming?
For only a short amount of time. They were assuming that there's no friction or anything.
Yeah, that's another big key here. No air resistance or friction between the bearings and stuff on the wheels and the trucks. So a lot of energy loss that we're not accounted for in this problem right now. We will account for it. We'll see it in the lab today, and we'll see it in the later example today.
So with the equation for kinetic energy, you know how it has the velocity in it? How do you know which velocity you're going to use? Does it?
Depends on the part of the problem.
Okay.
If I'm in the beginning of the problem and there's kinetic energy, I call it 1/2 mvi squared.
Okay.
If it's the end of the problem, like this example at the bottom of the ramp, and that's where I'm using kinetic energy, it's called 1/2 mvf squared. So Chris asked the question of, do we drop the plus or minus? Because it asks for speed, speed is always positive, so it's got to be the positive answer. But it is good to recognize in a problem like this, since this object is going down the ramp like this, its velocity is components again. It's going to the right and down. So we wouldn't really be giving a positive or negative answer. We'd be giving an answer with an angle. Remember the angle, the directional? So I wouldn't be worried about it in this problem because of that. But because it says speed here, we know it's going to be a positive answer. Okay, we know that has to be.
Is there any time we should be worried about giving like a negative?
The only time you might be asked about the directional would be when we're doing stuff with vectors. So on your midterm it could come up, but not for this test.
Alright, that's something like this.
Yeah, but not for this test. It won't.
But what if it's
Sometimes I add things from test to test, but that won't be. I won't combine vectors with this.
So if you know it's going just horizontally or just, then
Well,
you can figure it out.
Yeah, that's assuming the skater's already on the ground. But at that exact moment, they're still going at an angle. You know what I mean? Where the ramp contacts the ground, they're still kind of, except this scenario, because this is kind of tangent. So in that case, it would be in the positive x direction. But here, it's at an angle. Okay, it's still at an angle there. Let's go to the next example here. So we're back to this concept of a pendulum bob here. And the pendulum bob, why can I not zoom in and out? This is so annoying, the settings. The pendulum bob is released from a given height such that the speed at the bottom of the path is 3 meters per second. What is the initial height of the bob, and at what height will the potential and kinetic energy be the same? The word bob is used a lot, so you're going to have to kind of get used to that. Bob means object on a pendulum, suspended from a pendulum, so from a rope. So let's take a look at this example. It's released from some initial height. And we're talking about it at the end, or meaning at the bottom of the path. It's released from some initial height such that the speed at the bottom of the path, so the velocity at this instant is 3 meters per second. The height at this instant is some value h. The velocity to start is 0. Why is it 0 to start? What's the key word? One key word. Released. Released. If an object is released, it means that it's being held back. It's not moving currently. It's either being compressed against a spring and then released, or held in the influence of the gravitational field on the Earth and then released. Okay, so its VI is 0. So in a problem like this, I have to consider, again, what my ground level is and where the beginning and the end of the problem is. Now, if I look at the wording, is there anything to do with the object after it reaches the bottom of the path? Does it say anything about coming back up, how far we'll go back up, or to what height after the bottom of the path? Anything like that at all you see? So you can assume that the beginning and the end of the problem is what we've drawn in the diagram here. Initially, it's at a given height, and at the end, it's at the bottom of the path. So in this problem, we have the beginning and the end. So it would make sense for me to call the bottom of this path ground level. Okay, it would just make sense for me to call that ground level. And then this problem is just the same as the last problem. So we have a skateboarder going down a ramp. We have an object falling, free fall. We have, in this case, a pendulum swinging back and forth. In all three of those cases I just mentioned, it's the exact same setup. PE in the beginning equals KE at the end. Literally, it's the same exact setup again. If I were to drop an object right now, like you saw with the data table, it had PE in the beginning, didn't it? And when it hits the ground, it's got all kinetic energy and no potential at the bottom. It's the exact same arrangement in this case. So my problem, again, is the same thing. I start with conservation always. I recognize the beginning of the problem. It has height, so it's got potential energy. Does it have any kinetic energy in the beginning?
No.
Why not?
It's being released.
Good. Its velocity is equal to 0. It's being released. And then at the end of the problem, it no longer has height. It's at what we're calling ground level. We know that the pendulum is not hitting the ground, right? It's not physically the ground there, and the pendulum is coming by and smacking the ground over and over, because that would cause energy loss, like you saw with the bouncy ball. Right? The bouncy ball didn't get back to the initial height, did it yesterday? I hope it didn't. You know, if you dropped it appropriately from rest, the bouncy ball did not make it back up to 100 centimeters. The idea behind that is the collision is losing energy, and we'll talk more about that. This pendulum is not hitting the ground. So all the energy it started with is all the same energy at the end. But at the end, that energy is now the energy due to motion. So it's kinetic energy. So this is the exact same formula as example number 1. The only difference, what are we solving for here? Height. We are trying to find the initial height in this problem, so we're searching for yi instead of vf. What is vf in this problem? What is the velocity at the end of the problem here, Daniel?
3 meters per second.
3 meters per second, yes. This is your final velocity right here. I didn't call it VF, but because this is the end of our problem, it is inherently VF. Our problem begins at the top, ends at the bottom. Afterward, we don't care. It will oscillate for a while, but we don't care about that motion after it reaches the bottom of that path. So this equation, what happens again in both cases? What cancels? This will happen a lot in this chapter. It happened in last section, 6.2, with the sliding problem. The extra credit problem I've given you, the sliding problem. By the way, that extra credit is due on Friday if you want to do it. You could use that video vernier program that I mentioned yesterday to measure the velocity of you as you slide, as long as you have a meter stick or a ruler. You can put a ruler in the background also. That works too. And just set that distance equal to 1 foot instead of 1 meter. But that's a useful technique for that. So in this problem, I'm looking for y. So divide by g on both sides. Can we all do that? I think that's reasonable to ask. Last problem, I went ahead and I plugged in numbers. But here, I think it is reasonable to say that everybody should be able to isolate y. To isolate y, you simply divide by g. You divide by g on both sides. So what is the initial height of the skater, or this pendulum rather, of the pendulum, if it has a velocity at the bottom of 3 meters per second?
0.46.
That looks great. Okay, 1/2 of 9 is 4.5. 4.5 divided by 9.81 should be around a half. That sounds reasonable to me. So we're only talking, by the way, a half a meter, right? Human beings, adults, around 2 meters. Not really, by the way, not everybody. But a half a meter is about this tall right here, right? A meter stick would go up to about here. You saw it yesterday, but a meter stick went to about here. So a half a meter is right there. Okay, so you have an idea of the number, the value itself. So for a pendulum like that, if I released it, which I did the other day from about a meter up or so, it's going to be traveling way faster than 3 meters per second at the bottom because I'm giving it more energy by raising it up further. Okay? 2. In example 2, the second part says, at what height will the potential and kinetic energy be the same? It's a great question. At what height will the potential and kinetic energy be the same? If I start with 10 joules of energy, and they're the same, what will they each be?
5.
5. Right, 5. So I have to lose half my height to get my potential energy to be half. So the answer is the halfway point. So in this problem, at what height? The answer is 0.23 meters. Half of this answer. Whenever your potential and kinetic energy are the same value, right? At what height will they be the same value? It's the midway point, assuming the object is dropped from rest. Is dropped from rest. So you take the potential energy that the object has to start, and if you want to find half of it, just find the height point that's halfway. Thank you, David. Okay, the answer is halfway there, halfway. I was going to make a joke, but it's not funny. All right, let's go on. So, a diver leaves a diving platform in this example. Leaves, moves away from, we don't know the velocity yet, at an angle of 23 degrees, oh here it is, with a velocity of 4 meters per second. If the platform is 8 meters above the water, what is his or her speed the instant before hitting the water? So we again draw a diagram. The diagram does not need to be elaborate. Diver, water, done. Now, the diver leaves with velocity. With velocity. It's not released from rest. It's not starting from rest. It's not dropped. It leaves, he or she leaves the platform with velocity. Therefore, what kind of energy does this diver have to start?
Kinetic.
It's definitely kinetic to start. Because the diver leaves with a velocity. As soon as we see that, we know that there's got to be kinetic energy. But the diver is also at a given height to start. So what other type of energy params does he or she have? Potential energy. Okay? That's my information to start the problem. Now, what's the end of my problem? Alex?
He hits the water right before he hits
Good. The instant before he or she hits the water. So here is the end of the problem. What kind of energy will the diver have at that moment if we call the water ground level?
Kinetic.
Only kinetic. Good job. Only kinetic at the end. And the key is to recognize I need to call this ground level. Okay, I need to call that ground level for that to make sense. Yes, I get it that the pool water level is not technically the ground, right? That's the water surface, and then the actual pool is deeper than that. So I know that there's a ground, physical ground, below the water level. But I'm looking for the end of the problem to be the water level, therefore I call that ground level. Again, you can be like, you want to do it differently and make a hard case out of it, you can, but it's adding work. So I would recommend that you take my advice on these problems. But you could do it and call the bottom of the pool ground level, and then call the height of the pool maybe 5 meters or something, whatever you want to call it, and redo the whole problem. But then you tack on potential energy here, and it changes the potential energy up here, because now you have this additional height. So it doesn't make sense not to call this ground level. You just do it. It makes sense. Okay, the height of the platform is given as 8 meters. We know that the velocity initially is 4 meters per second. We know we've got an angle of 23 degrees. And we're looking for the velocity at the end of the problem here, when the diver impacts the water. Now, Here's the great part. It's the best part about energy. It makes it so much better than kinematics. If I'm given a speed and I'm trying to figure out the kinetic energy of the object, it doesn't matter what the components of the speed are. It doesn't matter that this is at an angle. Sure, there's VIY and VIX, and we've talked about that with two-dimensional projectiles, with projectile motion. There's VIX and VIY. But because kinetic energy is 1/2 mv squared, that v is really the speed of the object there, even though it's v. So we don't have to take into account, maybe jot this down, this piece, we don't have to take into account any sort of angle of launch or landing. We don't have to take into account the angle where it is launched from or lands when it comes to speed. With work we do, with work we talked about that. It's FD cosine theta, the theta matters there. But with conservation of energy and kinetic energy, the angle does not affect the kinetic energy. The angle does not affect the kinetic energy. So the angle in this problem is extraneous information. It is not needed. I put it here on purpose, though, because some of your homework examples in the book talks about angles. But they also reference in the book that the angle doesn't matter, the same thing. But if you had homework and suddenly you have all these angles, and you're like, oh my gosh, I couldn't do it because I don't know what to do with the angles. So I made this an example this year. It doesn't matter, the angle itself. Okay? Now, let's talk about this formula. Well, here it is. It hasn't changed. Example 1, 2, and 3 are the same. Look at that. The same formula. Just like F equals ma was used for all force problems. Now, I replace it with the correct energies. What energy did we say the object had in the beginning of the problem? Prams. Yeah, good job, Prams. Potential and kinetic in the beginning. Because this person, this diver, is diving from a height with a given velocity. And then the diver lands at what we're calling ground level with only velocity, no height. So the diver only has kinetic energy at the end of the problem. So again, it's very similar to the last problem. What's the added note? What's the added part to this problem when compared to the last problem? What's the one major difference here? Is it?
There's kinetic energy at
The beginning also has kinetic energy. The last problem didn't have kinetic energy in the beginning. It was starting from rest or it was released, so it was only potential. Okay? So now in this problem, I go through the process. mgyi plus 1/2 mvi squared equals 1/2 mvf squared. What do we notice is in all terms? M. So what happens? Only because it's in all terms. Remember, the only time you can cancel a variable is if you divide through. Divide everything by that variable. And the only way it works is if that variable is in all terms. So the minute I involve potential energy elastic, 1/2 kx squared, no longer has mass in there, can't drop off mass. So it's important to make a note of this, that only when mass is in every term can it drop off. I carry down my equation. I analyze and I say to myself, okay, I'm looking for the velocity of the diver when he or she impacts the water, and therefore I'm looking for Vf. So this is a very easy one to solve algebraically also. Get rid of 1/2, multiply by a 2, and make sure that this whole thing, the left-hand side of the equation, is in parentheses right now. So multiply both sides by 2, and then take the square root. Or plug in numbers at this point and solve for Vf. Okay, again, if you're not as confident, I would recommend you plug in numbers. If you're really feeling confident, I would do what I'm doing here, which is multiply the whole thing by 2. And then after that, taking the square root on both sides. Again, recognizing that we're looking for the speed as the diver hits the water. So I don't have to worry about plus or minus in my final answer. I'll put it here still because I know mathematics I should. But my final answer will be the positive value because I'm looking for speed. So that's my algebraic approach. Again, where would you plug in numbers if you were a little bit confused right now? You would plug in where the green arrows are shown here. Okay, if you're a little bit confused right now, you're seeing the algebraic solution, plug in where you see the green arrows there. And you can go ahead and solve that equation for VF. Either way, you'll get the same answer, obviously. Okay, you'll get the same answer. Can I get a reliable answer from someone, please? Bridge? 13.15, rounding to 2. Agreeable?
Yeah.
All right. Okay, and again, I'm using the positive value because we're looking for the speed of the diver. What kind of an answer would not make sense here? Because speed, yes. Remember, it's plus or minus, so technically there is one answer, but we're rejecting it. What range of answers would not make sense here? Look at the beginning of the problem. I'll give you a hint. Look at the beginning.
Anything less than 4?
Anything less than 4 makes no sense. Think about it. Think about it. If you fall from a given height, but Tom Cruise again, remember Tom Cruise runs off a bridge? If you're running with velocity and you're falling down, you're only going to get faster and faster and faster and faster. So if your answer were less than 4, it wouldn't make sense. It would make, what that would mean is you put a negative sign somewhere wrong. Add a negative sign somewhere here or there or somewhere along the way. Then it would reach equilibrium, which means it would still have a higher value. Yeah. It could be, sure.
What
Yeah.
if the wind was like so strong that I actually was
Then that's different. Yeah, that's absolutely different, man. If you're a parachuter, right, a parachutist coming down, or paratrooper, I guess is the right phrase, and you're descending toward the ground, you could control your speed with different, mechanisms, I'd say. But the actual uplift from the air could cause your speed to slow down and then speed up, and that's different. But again, we are assuming in these problems, unless given information, that there is no air resistance. Now, you know what else this problem could extend to? This problem could then say, you know what this problem could say, ready? With this velocity, when the diver impacts the water, find out how much work is done to cause the diver to come to rest once he hits the water. So the diver hits the water slows down the diver until the diver stops toward the bottom of the pool. And it can say something like, how much work is done on the diver by the water to slow him or her down to rest. And then you would use the work kinetic energy theorem from section 6.2. You have kinetic energy to start because you have velocity, so you have kinetic energy. If the diver eventually stops, there's no kinetic energy at the end now, and you can find the work by doing work equals delta KE from section 6.2. I'm trying to explain to you guys that there are expansions to these problems so you can get an idea of questions you could see maybe on like a test or on a problem set type problem. Let's go to back to example 4. Yeah, Dan.
For example 2, did we skip B?
We did, you're right, Dan. Sorry. Go back to example 2 real quick. Thank you. All right, so back to example 4. Example 4, you want to shoot a rubber band across the schoolyard, the junkyard in this case, from an elevated window. So that's like 7 meters, that'd be like the second floor. At a classmate who's about 2 meters tall. You know that you can stretch the rubber band a given distance of 10 centimeters. That's reasonable, 10 centimeters. The rubber in the rubber band has an elasticity or spring constant of 0.2 newtons per meter. With what speed will the rubber band hit your classmate in the back of the head? With what speed will it hit your classmate in the back of the head? Now, a bit of a more elaborate problem simply because of the arrangement. So let's go ahead and start with a diagram over here. So here you are. Here's the ground. Here's your classmate. It's important to draw your classmate in this problem because your classmate has what?
Height.
Your classmate has a given height. That's important. Here are you, right up here. You've got no height. So you were at the top of this window, which is 7 meters above the ground. Your classmate, his or her head is 2 meters above the ground. Where will the problem end? We know it begins with you up at the window shooting the rubber band. That's where it begins. Alex, where will it end?
When it hits your classmate.
Yeah. So what height below where it started will it end, Alex? What height below where it started will it end?
5 meters.
5 meters. So we are calling this is not drawn to scale, obviously. I know it looks like half the height. We are calling this ground level. So the important height in this problem is actually 5 meters. And this is our ground level line right here. Again, it's really important to recognize in this problem that we know where ground level is. You can call ground level just ground level. That's fine. But then when the rubber band hits your classmate in the head, it's still going to have potential energy. We have to account for it. I'm going to make it easier and call that dashed blue line ground level. So when the rubber band hits your classmate, sure, it's going to fall to the actual ground afterward, but when it hits your classmate, that's the end of our problem. I know we want a break. I'll try to give you guys a little break when you have your lab and take a minute while you're working on your lab. So in this problem, I need to recognize the types of energy that the object has in the beginning and again at the end. The end is the easier part. It's moving physically, and we're asked for what is the speed that it hits the back of your friend's head with. What is the speed? So what are we looking for, or what kind of energy is there at the end of the problem? Kinetic energy. Here's the rubber band. I'm going to draw it with a dot again on the diagram, hitting your friend in the head. And it's only got kinetic energy at the end of the problem. Whatever path taken, it could be a curved path, it could be a straight line, it wouldn't be curved technically, but it doesn't matter. Now, the problem is a little bit tricky though in the beginning. Once you release the rubber band, it has velocity. But we know nothing about the velocity with which it has when it's released. All we know is how far you've pulled the rubber band and how far above the ground the object is. What two types of energy are those? What two types of energy are pulling a rubber band to launch it and starting at a given height? What kinds of energy are they?
That's potential, right?
Good. And then what kind of potential is that we called that? What was the subword for that? Elastic potential. Good. For the rubber band. And then because the person has height, regular potential energy that we've been talking about. So at the beginning, this person has potential energy due to height and potential energy due to the elasticity. Notice what I put as a subscript there, please. Potential energy initially is just mgy. And then PEE initially is 1/2 kx squared. That is a formula we went over in section 6.2 that you need to have understood to understand this problem. So again, the arrangement is the same. That's my starting. Oops, I wrote it backwards. I don't know why. It doesn't matter, obviously, right? But I have no idea why I decided to write that backwards. So in the beginning, this object has two types of potential energy due to its height, that's mgyi, and due to its elasticity, its stored energy because it's being stretched. At the end, the object only has kinetic energy. So again, I want you to recognize something in this problem. It's really no different than example 2 and 1 and 3 that we just did. The only difference now is what is the new type of energy that we're accounting for?
Potential elastic.
Elastic potential energy is the only new thing we've introduced. That's it,
Elastic.
right?
Potential energy.
The only new thing, but, listen, But we have to also recognize that mass can no longer cancel out. Write yourself a note that as soon as you add something on, we're going to talk in the lab about what's called Q loss. Once you start the lab, I'm going to pause you and talk about it more. In the last example of these notes, we'll talk about Q loss. Once you involve Q loss or elastic energy, and you're not just doing potential and kinetic, you can't drop off mass. You can't drop off mass because it's not in every single term. That's the reason why. Okay, because it's not in every term. So in this problem, we have to, in your AP exam, in this problem, you have to go ahead and solve again for VF. This is a little bit more complicated to solve algebraically. You got to double it, get rid of 1/2 and multiply by 2, divide by m, square root it. It's a little bit of work. But you know what else you got to do? You got to look at your units for all the values. Mass, unfortunately, is given as 3 grams. Can I keep it that way? I can't make it 3 grams. What's my mass really? Yeah, kilograms. Next, I know my initial height is not 7 meters. It's 5 meters because we're seeing how far above the person the sling shooter is. We know that the rubber band is stretched a distance of 10 centimeters. But I don't want centimeters. I always want meters. That's 0.1 meters. And then finally, the K value is given as 0.2, and those units are perfect, newtons per meter. So my givens are on the far right here. I have to make sure that I understand why they are altered the way they are. Mass always in kg. Length always in meters. K always in newtons per meter. You can't go wrong if you do this each time. At this point, it becomes plug and chug. I know what I'm saying that is it's easy and it's a lot, but it really is algebra. It's actually just arithmetic once you plug the values in. Okay, but this is a simple combination of algebra and arithmetic. But you gotta plug in the right spots. You gotta know what each thing is. So I'll do a quick plug in so you can see it. I'm dropping units because I've already verified my units are correct. Bless you. Okay, again, looks complicated, not at all complicated if you have a calculator next to you. Okay, really not complicated at all. I'm going to give the answer. You can obviously check this yourself, but I do want to start the lab, which is why I'm going to give the answer instead. It looks like I'm getting around 10 meters per second. 9.94, I think. And again, we're looking for the impact speed, so it's just the positive value. The impact speed is the positive value. I want to make a point. So I know some of you are calculating, but pause your calculations, just quickly look up. Quickly look up. Listen to what I'm going to say to you. Ready? If I told you that air resistance caused